just a bit of motivation, maybe I'll just say this orally. So I'm sure you all know Cayley graphs. So remember that Cayley graphs are graphs constructed from a finally generated group where you take as the vertex set just all the elements of your group and then you connect any two elements if you can go from one to the other by jumping via your fixed generating set. And so there are many nice connections between properties of the Cayley graph and properties of the group. And I'll just give a few just to motivate my talk, and I'm going to use them later. So Cayley graph like this. G, so G is a finally generated group, generated finally by the set S. And so there are various flavors of properties that one can capture using the Cayley graph. For instance, analytic properties of the group, so such as amenability. Amenability is equivalent in the geometric world to the Cheeger constant of your Cayley graph being 0. So I'll just remind you what the Cheeger constant is. So if you have a graph X, you can look at a finite subset f in X. And you can look at the boundary of a subset of vertices. So all the edges that you have to cut through to remove f from your graph. And if you divide by the number of vertices in your set, this quantity, if you take the infimum over all such finite subsets, this quantity measures how well connected your graph is. And so this is called the Cheeger constant of your graph. And if this Cheeger constant is 0, so G is an infinite group, let's say, if this Cheeger constant is 0, then a group is amenable and vice versa. So, the Cayley graph being not that well connected means a group is amenable. And of course, there's the famous theorem of Gromov, which says that so another geometric invariant we can look at for the Cayley graph is growth. Okay, we can count the number of elements in a ball of a certain radius, and we can see how this number grows with the radius. And if this number grows polynomially, then Gromov proved that this is actually equivalent to the group being virtually nilpotent, so having a nilpotent subgroup of finite index. And this is very nice because being virtually nilpotent is a completely algebraic property, and we're able to characterize it in this completely geometric way. So we have this kind of a nice dictionary between algebra and geometry. Okay, so that's just motivation. I'm sure that's something you all know. And so, as I said, here we need G to be residually finite, but what if we know more about our group? What if we know that our group is also, for example, we know something about the structure of the subgroups of our group, or some other algebraic information? So now we're going to always think about G being finally generated as before, but we're also going to look at groups with a lot of finite quotients. Okay, so we want the structure of finite quotients to be sufficiently rich in order to be able to detect things about G from these finite quotients. So we're going to take G to be residually finite. Residually finite, if you recall, who doesn't know what residually finite means? Anyone? No, okay, so essentially you have a lot of finite quotients, in particular the intersection over all the normal subgroups of finite index is trivial. And so in this case, we always know that we can take, for example, a nested sequence of normal subgroups of finite index. I'll write it like this. Nested sequence of normal subgroups of finite index of our group such that the intersection over all these subgroups is trivial. We can always do this, and we can take various such sequences, and we'll call such a sequence a filtration. what we'd like to be able to do is we'd like to be able to construct a geometric object which encodes some of this algebraic structure which we have, which we know about subgroup, in a metric space. So this is where the term box space comes in. So the box space of G with respect to the filtration and I as above. We'll write it as follows. So the box space is simply, as a set, just the disjoint union over all the finite quotients by these subgroups in our filtration with the metric. So we liked it to be a metric space. So as a set, it's just the set of finite quotients, and the metric that we take is the following. And we specify two things about this metric. So first of all, on each finite piece, we'd like the metric to be just the Cayley graph metric induced by the Cayley graph metric on G. Okay, so we fix some generating set for G. G is finally generated, and then we look at the induced Cayley graph on the quotient. Okay, so now I've told you what the metric is on each piece, and now I just want to put my quotients very far apart from each other, so that the geometric properties of each of the quotients don't really interfere with each other. So I want the distance between any two different finite quotients to be, let's say, the sum of the diameters, something like that. It doesn't really matter how we choose this distance as long as it goes to infinity with the indices of our subgroup. Okay.
And just a quick question, when you want these diameters, I guess the idea is that you want to make sure that an element is not closer to something in another quotient than it is to anything. Okay.
Exactly. So the point will be to study, I'll use the space over here as well, so the point is to study the properties that all these quotients have uniformly. Okay, so properties. So allows us to study the geometric properties of finite quotients uniformly. Okay, we'll say more about what we mean a bit later. So another nice property is that just as with Cayley graphs, we know that changing the generating set doesn't change the Cayley graph too much, it only changes up to quasi-symmetry. And in this case, if we take two different generating sets, so let's say, I'll just denote like this, the box space with a fixed generating set S on G, then we actually know that the box space, if you take a different generating set but the same sequence of subgroups, that's crucial. So if you take some S prime, then the box spaces will be coarsely equivalent. Now, coarsely equivalent. So coarse equivalence is it's almost like quasi-symmetry, except so in quasi-symmetry, when you look at the image of your metric space, you want that the distances be deformed in a linear way compared to the original distance. Coarse equivalence is almost the same thing, except you allow yourself different functions, not necessarily linear functions, to be able to deform the distance. Okay, so this is the kind of the correct notion of two spaces being equivalent in this this category. Okay. So that's nice. Another nice property is that we do, in some sense, recover the Cayley graph structure, because what we have is that for all R, since we have this nesting of the subgroups, actually our quotients are getting bigger and bigger, and on bigger and bigger balls, they're looking more and more like our K graph. Okay, so for all R, there exists some n such that for all I bigger than n, the balls of radius R, in the quotients with the box space metric are actually isometric to balls in the Cayley graph region. Okay, so we're recovering some of our Cayley graph structure in this metric space. And okay, so that's kind of the motivation for looking at this object. And as you might expect, this object might be able to capture more things about our group than simply the Cayley graph. Okay, we're also somehow incorporating some algebraic structure into this object. Okay, so let's give some examples of let's give some examples of how this captures properties of our group. So again, let's have a little table. So first of all, the reason I mentioned amenability is that we can also find a nice property of the set of these quotients, which completely captures this notion of amenability for the group. So I'm not going to say too much about this later in the talk. So this is something called property A. This is kind of you should think of this as a non-equivariant version of amenability. And it allows you to recover amenability for the group just by averaging this property out on the quotients and then taking a limit. And I think this is possibly due to Eric, but you can find it in the book of John Rowe, called Course Geometry. Okay, so that's just to kind of give a parallel with what we had of says. Another way these box spaces are interesting is that they allow us to give the first example of an expander. Say what an expander is in just a second. So if we take a group with property T, so in other words, a group which cannot act well on a Hilbert space, then the box space will actually form an expander sequence. So if you recall what I said above about the Cheeger constant, so an expander is simply, we have a sequence of finite graphs. We say that the sequence is an expander if the sizes of the graph, so the number of vertices, go to infinity, the degree of the extend is uniformly bounded across the sequence. Some D, let's say, well, let's some D, so they're all of bounded degree, and finally the Cheeger constant. So it's defined slightly differently because I'm looking at finite graphs here, so I need to take the infimum over all subsets. I don't want to be able to take the whole subset because then I don't measure anything about the connectedness of my graph, right? So I want to be able to just take the infimum over subsets of size at most half of the graph. Okay, so I want it to be an epsilon which uniformly bounds the Cheeger constants of my graph from below. So all of them are highly connected. Because of these connectivity properties, these graphs are often used in computer science and other things which sound good on grant applications. Okay, so and this was actually an open question for a while whether these such sequences actually exist. Okay, we know that they have these useful connectivity properties, but do they actually exist? And the first proof that they exist was actually probabilistic in nature. And the first actual explicit construction was given by Margulis in the form of a box space of a group with property T. So take something like SL3Z, then your quotients will.
Can you reformulate that definition just in terms of the box space rather than in terms of the sequence? Does that make sense?
I suppose you can, but I mean, essentially, you should think of the box space as just allowing you to.
But the reason I ask is because that's how I think about things all the time, but I never think about box spaces. So
I see. I mean, in some sense, putting them all in one space, it just allows you to phrase certain properties in an easier way. Certain properties, it's easier to say just the space has this property, and then it allows you to not say things about. I mean, I'm sure you can rephrase it, but yeah.
So even though this is a completely sort of graph theoretic description, the first examples came from box spaces.
They weren't the first example of expanders.
So SL, the box spaces of SL3Z were the first.
Constructive, right? So
Yes, exactly. Yeah. I mean, I guess when we say example, we
Oh, right,
mean,
okay,
constructive.
very
Yeah.
explicit.
But the first proof that expanders exist was non-constructive and
Yeah.
was given in a probabilistic way by Pinsker.
But wow, okay, this seems bizarre. Like that's a pretty sort of specific construction, and this is a very sort of open definition. I find it amazing that that's the first time someone construct one explicitly.
Yeah, sure. Yeah, and you know this kind of is good for group theory. You know, the fact that we can provide computer scientists with all the expanders that they might want using property T groups. Okay, and so just another property, just to kind of draw a parallel between the Gromov theorem, which I mentioned above. So I'll just say, is there? Yeah, there's a. I'll just say. So one thing, instead of looking at the volume of balls as we did with the Cayley graph, we can look at diameter conditions for these graphs for the finite quotients in the box space. So we can see how the diameter grows with respect to the size of the quotients. And so Broyard and Toynton were able to show that if the diameter grows as a power of the size of the quotients, so this means that we're very far away from the world of expanders, because for expanders, because of these high connectivity properties, the diameter of the graphs in your sequence must grow logarithmically with respect to the size. And if you impose a strong negation of this, so if you impose that actually your diameter grows as a power of the size of your quotient, then you can actually show that your group admits a virtual surjection onto Z. And this is what Broyard and Toynton showed using the theory of approximate groups. So this is a very, very deep result. And you can think of this as a kind of analog of Gromov's theorem for box spaces. And you can actually show the opposite implication as well, which is a lot easier to show, and this is what we did with Valette. I'll mention more about that work soon, so actually we have an equivalence in the same way as the Gromov's theorem. Okay, great. So just a word of warning for box spaces, the sequence which we choose matters a lot. So we can actually have different choices of these sequences which give rise to very different properties in the box space. So in fact, with my collaborator Thibaut Delaby, we actually showed that you can have, so wave my hands for this, so we showed you can actually have a nested box, a meshed box space. So you can actually have two different sequences of subgroups which, form this kind of structure. So I mean, one is contained in the other one, and then you have no, do you know what I mean? Yeah. Okay, so it's meshed, and so this sequence always sits inside some element of this sequence in this way, and we actually proved that you can find an example of this where the box space with respect to one sequence embeds closely into Hilbert space, which is very far away from expanders, and the other one contains a relative expander, which is an obstruction to embedding into Hilbert space in a nice way.
So mesh there, did you mean that for every I, there's a J, so that the X?
Yeah, so I just mean, N1 is N1 contains M1 contains N2 contains M2.
Okay,
so
very
really,
strong.
yes, it's very strong. Yeah. Okay, yeah. So this is kind of this is different to say per finite completions where such a thing will not make a difference. Okay, so now moving on to the main topic of my talk, which is rigidity. So, as I said, you can ask questions, how does the box space vary according to the subgroups that you take? You can also ask, how rigid are box spaces with regard to the group that you take. So, for K graphs, we know that you can have quasi-symmetric K graphs, which come from really different groups, non-commensurable groups, for example. So the question is, once we impose this algebraic structure into this geometric space, what can you say about the groups, given that the box space is of course equivalent? So the question. Suppose we have two different box spaces, which are of course equivalent. So we have two groups, G and H. What can we say about the relationship between G and H? Okay, so here I'd like to draw a kind of parallel with an old question of Remesennikov, which asks, can you recognize a group from the set of its finite quotients up to isomorphism? Okay, so for example, this question of Remesennikov actually is still open for the free group. So suppose you have a residually finite group such that all of its finite quotients are the same, the set of its finite quotients up to isomorphism is exactly the same as that of a free group. Can you say that this group is free or not? And so progress has been made in various classes of groups. For this question, for example, some progress was made by Brightson, Konda, and Reed on this question, who did it for a certain geometric class of groups. And I like to think of this as a kind of geometric version of this question in some sense. We also have the geometry, so maybe we can say a bit more. And indeed we can. So first kind of theorem in this direction, which we did with Alain Valette in Neuchâtel. We showed that actually, and this is what one would expect because we have a geometric relationship between these spaces, and that actually does imply a geometric relationship between the groups. So we can actually show that the groups in this case will be quasi-symmetric. And this in itself is not very surprising, but it does lead to some nice applications. So question of Mendel and Naur. Asks how many expander graphs are there? Okay, so we know we can construct expander graphs from groups of property T, for example, or we have also other ways, combinatorial ways of constructing expanders, such as zigzag products and such, and but we don't actually know that they're all different. So the question is, how, are these expanders all different? Maybe expanders coming from property T groups are different from those not coming from property T groups, which is the case. So this question was open, and some progress was made on it by David Hume using a different method. So I'll just say Hume. He used separation profiles to show that there exist infinite many coarse equivalence classes of expanders of large girth. So those for which the size of the minimal loop tends to infinity. And
yeah, it seems cheating, right? Because what the separation profile captures is precisely this set of distances you affect between different pieces. Precisely what you would like to ignore, right?
not sure I know what you mean.
He's saying depend on that choice of when you made that sum of diameter choice.
I see. I mean, David Hume did it just for expanders. He didn't really talk in terms of box spaces. He just spoke in terms of the components.
Okay.
So, okay, maybe we can
I'd
take it up
like to
later.
discuss this later on.
Yeah, I'll just mention.
I don't understand that. I don't remember properly. Go ahead.
Okay, I see. So the point is that actually we can show this very easily using this result, because one can simply take groups which are not quasi-symmetric and then get expanders from them which will not be quasi-equivalent. So maybe your question was about the choice of distances between the components.
Yes.
And so actually what we show here is that we show something slightly stronger, is that, well, I mean, regardless of the distances which you place on the components, when you have a coarse equivalence between two such spaces, this actually gives you uniform quasi-isometries on a large number of pieces in your box space. So the choice of distances between the components really doesn't matter.
In fact, I made a mistake. What I had in mind is the sequence, and if you replace the sequence and by a subsequence, then this changes drastically the box space, right?
It depends. It depends.
And that's precisely what you detects. My recollection is that you start with one sequence and simply playing by choosing different subsequences gives spaces that he's able to distinguish.
Ah, I see. Okay.
Right.
I see.
And so that's a little bit disappointing, right?
I see what you mean. And so yes, and in fact, I'll mention that again a bit later, because we also have an easier way now of doing such a thing, if this is what you say he did. But okay. But anyway, so we'll come back to that later. But I just want to say, so using this result, so now we can show that there are infinitely many coarse equivalence classes of expanders coming from, say, property T groups. Okay, so we have many property T groups which are not quasi-symmetric pairwise. So, for example, if we take SL and Z for different n, Eskin proved that all of these groups are pairwise non-quasi-symmetric. And so now, if we take any sequence of subgroups and construct box spaces of these SL and Z of different n, we get non-causally equivalent expanders from these. Okay, so that's just
Can I
yeah.
ask a question about with Alan? So are you saying that for any sequence Ni and Mi you have a coarse equivalence, or for every possible sequence?
for any. So once you have such a coarse equivalence for some Ni and Mi,
Then you've always got.
then you have this quasi-symmetry. So essentially this shows that the box spaces really are very, very rigid, and we'll see in a second that they're even more rigid than that.
But box space depends on the sequence?
The box space depends on the sequence.
Even
yes.
if sequences are confined to each other?
Yes.
Confinable to each other.
Yes, in fact, I'll give it a very interesting examples which really diverges from the case of.
So, which means that box space cannot be associated to the profiling completion.
Exactly, yeah.
Right.
And just a question, quasi-isometry, can you say something about coarse equivalence of box space? If two groups are quasi-symmetric, does that automatically mean that you have?
No, because I mean, I think in general you can't. It's very difficult. I mean, to get the box space, you need this large subgroup structure, and in general, you can't really get this just from simply a quasi-isometry. And
Well,
maybe you can in very specific cases, but.
So, for instance, I mean, certainly one could be residually finite and the other one could have no finite quotients at all.
Yeah.
Well,
But even if you're looking in the set of residually finite groups, I think you'd be hard pressed to actually squeeze a sequence out.
Even with the same group, right, you can get coarsely embeddable ones. And you
Right.
can
Yeah. I mean, for example, yeah. I mean, yeah.
Okay.
Exactly. Okay, let's try to switch up the boards. So if I write here, can everyone see? Yeah. Okay, so oh yeah, and I'll just mention another result in this direction, which was obtained by Kajal Das, who was a PhD student from Anastasia, I think is now in Israel. So he managed to prove that, and the proof is much more deep than the proof we have with Alam. So just compare with the result of Kajal Das, who proved that if you have two closely equivalent box spaces, then the groups are actually uniformly measured. Great. Okay, so we have this result concerning the rigidity of box spaces, and but as I said, it's not that surprising because we're still getting a geometric statement at the end, and we're assuming geometric information for the box space. And what we'd like some kind of structural, maybe algebraic rigidity. So the question is, can we do better? By this I mean, can we give some kind of algebraic conclusion for our groups G and H? And it turns out that we can, so now I'll pass to joint work with my collaborator Thibaut Delaby, who's also in Neuchâtel. And here we're going to work with, the topic, to look at coarse fundamental groups. This is joint work with okay, so just as a kind of slight diversion, it's back. Just as a slight diversion, so in what way, in order to be able to prove some structural equivalence between G and H, one thing that we might ask ourselves is, to what extent can we recover the subgroups that we use to construct the box space? And that's a fairly natural question, and so for this, I'll just mention that, so in general, when you have a free group, when you look at the, so at some quotient of this free group by a normal subgroup, how can you recover the normal subgroup? Well, you can simply look at the Cayley graph of this group, and you can look at the fundamental group of the Cayley graph. Okay? Now, when you look at this Cayley graph, the labels along loops in this Cayley graph are exactly the elements of n. And when you look at the fundamental group of this Cayley graph, you recover actually n. Okay, and this
Up to isomorphism.
up to isomorphism, yeah. Up to isomorphism, and so this works well because we're in the case of a free group. So the fundamental group in general of a graph, and this is the case we're in, is always free. So this doesn't recognize if instead of the free group Fn here we had some other group, we can't just apply the fundamental group because we're still going to get a free group. In fact, we'll get the kernel of the map from the free group to that quotient, right? So that doesn't work for trying to recover the sequence. So what we'd like to do is we'd like to introduce a coarse version of the fundamental group, which can hopefully recover these subgroups in certain situations.
I just want to clarify this one. So you're trying, I mean, somehow you want to just recover them as isomorphism
Yes.
classes rather than as, I mean, another thing you could just, I mean, somehow that's the same as, in this case, that's the same as knowing its index in Fn, which is actually just the same as the number of vertices.
Yeah, I mean, in FN you get a lot more information, and actually we'll see that by applying what we're about to introduce to free groups, you actually do get a lot more information. You get lots of interesting examples exactly because of this rigidity of the subgroups of the free group. Okay, so what we'd like to do is we'd like to introduce a coarse version of the fundamental group, and this is actually this was first introduced by Barcelo, Kramer, Melvin Bacher, and Weaver, and there's also a nice paper by Barcelo, Khukhro, and White about this. So they introduced a very general notion of the coarse fundamental group, but we're just going to specify it to our setting which interests us. So our setting is as follows. We'll have a finite Cayley graph X, and well, to define the fundamental group, we need a base point, and there's an actual base point in our so in our Cayley graph X is just the identity of the group which this Cayley graph represents. And okay, so now I need to tell you what the paths are. So the paths are going to be maps from the set. So a discrete set from 0 to some integer LP, which will be the length of the path, to our space X, which is 1 Lipschitz. Okay, so that's what we now call paths. Okay, we're not in a continuous setting. We just have these discrete ways to move around our graph, and we're going to say that two paths P and Q are close if so either the lengths of the paths are the same, and surprise, surprise, the paths are close. Where, of course, by the distance, I mean just the distance in the graph. Okay, or another way of being close is in case the lengths of the paths are different, we allow one path to be exactly the same as the other path, but then to wait for the other path at the end. Okay? So this I'm not defining yet the notion of homotopy, which I will do using this definition, but for now we're just defining this kind of intermediate notion. So if the lengths of the paths are not the same, then we would like that for all indices less than the minimum of these lengths, we have that the paths coincide exactly, and then one path will just wait for the other path in the same vertex. Oh. Okay, so depending on which of the paths is actually still defined in I, we just set that the path waits for the other path in the same vertex. Okay, so what we should have in mind is just.
So they have the same endpoint.
Yes, exactly.
Well, they're exact. Well,
So that's what they do, and now, so since we want to define the fundamental group, we want to define a coarse notion of homotopy for our discrete paths in our graph. So I'm going to say that these two paths are homotopic. So I should probably mention that so R is just some constant that I fixed at the beginning, and then I'm going to define the fundamental group on that scale. Okay, so that's the purpose of R. The purpose of R will be, in the end, to be able to ignore small loops and to be able to detect the big ones, which will allow us to detect the subgroup. Okay, so two paths are homotopic if there exists a sequence going from a sequence of any length, n, going from P to Q, such that the adjacent paths are close. Okay, so basically you can jump from P to Q using R homotopic paths, R closed paths. And the fundamental group now is just the obvious thing, so denote it by 1R, so it's the fundamental group on scale R of X with base point. The identity is just the set of the loops base at E up to R naught. Okay, so why is this good? This allows us to jump over small loops. Okay, so on the scale R, we can actually jump over loops of length 2R. These loops will be trivial in our fundamental. So our homotopies can pass loops of let's say holes of size 2R. Okay, and actually we didn't really think of this at the time, but this is the same thing as gluing in small cells into your Cayley graph, so cells of size 2R, and then looking at the fundamental group of that. So somehow it's the fundamental group of a complex which sits in between the presentation complex and the Cayley complex. Okay, and so the theorem is that if we're in a finally presented group, and we take K to be the maximum over all the lengths of relators. So by here, by this notation, I mean the lengths of relators of elements in R in the free group on S. Of course, if we have a normal subgroup G such that following condition holds, so the twice this maximal relation length is smaller than the infimum over all the lengths of elements now with the induced metric on G in n apart from the identity. If if this holds, then taking just so that the proof actually works, taking R such that 4R lies in between these two quantities, so ideally you'd want these two quantities to be quite far apart, then the fundamental group on scale R of this Cayley graph loop space identity is isomorphic to N. So this gives us a way to recover the subgroup using this coarse version of the fundamental group. And now, so the way one should think of it is that just this fundamental group ignores all the loops which are small compared to the loops which are in N. So ideally you want to take subgroup N of very large index in G, then the relators coming from G, so the loops in your quotient which were already loops in G, are just trivial using this homotopy, using this fundamental group, and the only loops which you're recovering are the loops which give you your subgroup N. Okay, and so something to note is that so another property of this fundamental group is that when we take, so this is what we use in order to prove the following rigidity result, if you have two Cayley graphs which are C quasi-symmetric, so quasi-symmetric with constant C, then this actually gives us a surjection of the fundamental group on scale R of G onto the fundamental group of scale CR plus C of H. Okay? And obviously vice versa. Okay, and so this is what we use in order to show the following rigidity result for box spaces. So now, if we have two closely equivalent box spaces and G and H are finally presented, then actually I'll write it in this kind of slightly imprecise way. I'll write with the subgroups that we use to construct the box spaces that are isomorphic. What I actually mean is, so I'll say a remark first. So this uses the results of Alan and I as follows. So actually, as I mentioned to Pierre earlier, the coarse equivalence of these two box spaces actually gives us cofinitely many pieces in both of these box spaces, such that there's actually a bijection between these indices, and this bijection induces uniform quasi-isometry on the finite quotients. And so when I say that these two, so we get infinitely many, so we get cofinitely many subgroups in this sequence and cofinitely many subgroups in this sequence, and a bijection between them such that this is true. Okay, so essentially we're getting pretty much that most of the subgroups are isomorphic. Okay, so this uses this result, and it also uses hopficity. Of our groups. So in fact, since G and H are assumed to be residually finite, luckily they're Hopfian, and so are their subgroups. And so we can do this kind of quotienting procedure in both ways and obtain an isomorphism. It's only an isomorphism because our groups are Hopfian. So that's quite important. So in particular, this gives us that it gives us something stronger, but this gives us that G and H are just commensurables. So, which is exactly what we wanted. We wanted some kind of algebraic structural rigidity for our groups, and in the case of finely presented groups, using this kind of coarse fundamental group, we can get now not just a geometric statement about our groups, but actually a structural statement. And just in the last few minutes, I'd just like to give some applications of this. So just as with the result of Milan, we also have some nice applications of this. So as one might expect, this allows us to construct many different classes, coarse equivalence classes of various objects. I'll mention an application in this direction, but also gives us a slightly surprising, in any case I was surprised by this, this application. So this shows us that actually box spaces can behave quite differently to groups in the following sense. So there exist two filtrations of a free group such that the subgroups Mi are always contained in the corresponding Ni, and moreover, the indices of these Mi are uniformly bounded across the whole sequence. So we have some, let's say, A. So this is an A which is independent of I. Okay, so these sequences are very, very close to each other, but the box spaces which correspond to these two sequences end up not being coarsely equivalent because of this very strong rigidity result. So these two box spaces are not coarsely equivalent. And it uses exactly what Henry mentioned earlier, the fact that for free groups, we know exactly what the subgroup is when we know its index. And so this is different to the case of groups, because in the group world, we're very used to two groups differing by just a finite index, implying that the Cayley graphs are quasi-symmetric, etc., etc. And here we can see that, you know, even though the sizes of these relative quotients are bounded, we're actually getting different behavior in the box.
Can I just make sure I've understood that correctly? I mean, you say there exists, but it sounds like any, just choose any sequence Ni with sort of fairly big gaps in the indices, and then just choose any sequence Mi which is a fixed sort of distance down from the other.
Yeah, I mean, exactly, yeah. Pretty much anything works.
Yeah.
You just have to be careful that they're contained in one another,
Yeah.
and the indices stay bounded.
That's okay.
But yeah, essentially it shows you that for free groups,
There's
I mean,
loads
you
of
can,
those guys, absolutely loads of those.
yeah, exactly. Yeah. Okay, so that's one application which is surprising, and then just to finish another application, as I mentioned, so before we were using this rigidity to show that there are many different coarse equivalence classes of various objects, and now what we can show with this is that there are infinitely many coarse equivalence classes of box spaces of the free group on 3 generators. Probably doesn't matter very much how many generators, but this is a construction we give, which contain Ramanujan graphs. So Ramanujan graphs are expanders with the optimal spectral gap as you tend to infinity, and this unfortunately is not a course invariant, so you can have one expanded sequence which is course equivalent to a Ramanujan sequence without actually being a Ramanujan sequence. But what we've shown is that still, when you look up to course equivalence, you have infinitely many pods containing some Ramanujan expanders coming simply from the freedom of F3. And I think I'll stop there. Thank you.
Are there any questions?
In that theorem over there, do you have examples of infinitely presented groups for which the conclusion fails?
I think so, yes. So, yes, I think some box spaces coming from Reed products. I think we have this in the paper with Alan, so we have some box spaces of commensurable groups. We have some box spaces of Reed products which are coarsely equivalent because it's very easy to control when Reed products by finite groups are coarsely equivalent, and the groups are not commensurable. So yeah, in some sense this is optimal. We can only do this for finely presented groups because we have this Reed product.
Also using constructed examples with small cancellation.
How do you make sure that they're residually finite if you do it like that?
You do it in a Fourier series ways.
I know how you make sure that it's residually finite. I want to know how Cornelia makes sure.
Just to clarify, when you say up here in this theorem that the ni's are usually isomorphic to the mi's, you mean that there's some finite number of bits,
So
right?
some finite number of things you discard, and then you have a bijection between the components. I mean, between indices of the components, and this bijection by our result with Alan actually is a uniform quasi-symmetry for all of these components, and then this gives you this relationship between the fundamental groups, and then because of opticity, you can go the other way and then get
So that was true for, sorry, that's true for all sufficiently large I, not for...
No, so it's exactly, yes, true for all sufficiently large I. So essentially you should think of it, you have these two sequences, you discard finite subsets of these sequences for both of them, and then you have a bijection, which gives you this isomorphism.
And the bijection is N1 to M1, M2 to M2, and there's no permutation going on there. It's the sequences match.
Actually, no. It might commute a little bit. It might commute up to finite. Yeah. That's why I wrote in quotation marks.
Right,
Yeah, you might have a small permutation of the indices. Yeah, that's true.
Earlier, didn't you describe an example? Wait. You said if two different box spaces from the same group are always...
No, so they're not always equivalent. They can be very different. So in fact, with Chibaut in another paper, we construct examples of even box spaces which do this.
That's what I was trying to...
This thing, where one is coarsely embeddable to Hilbert space, and the other one contains relative.
Okay, but if you take the union of those two guys, then you have a filtration, right? If they go like this.
Yeah.
So, what does the union? Does it have?
So I guess
one
the
of those
union will
properties?
contain relative expanders,
Yeah,
thus
exactly.
will not embed into
Okay.
Hilbert space, but it'll have this
It's
big
some
part which behaves nicely.
filtration, yeah.
You have some mixed behavior.
So what was, I thought there was some statement at the beginning where something was called, there was some choice one could make and then the result would be to coarsely equivalent. But I thought
Generating set. The generating set for the group.
it's just changing the generator.
Yes, sorry, that's right. It's stable under the generator
Keep the
set,
filtration the same.
which is what you do.
Okay, right.
I mean, obviously, for certain groups, maybe I was going to advertise about Delaby's forthcoming paper where, so we've seen that this, we have this very weird behavior in terms of these bounded sequences. So in fact, it actually makes sense to investigate the situation in a more general way. So what maybe even though these spaces are not coequivalent, maybe you can still preserve some properties, and that's what he's doing in a forthcoming paper.
Are there examples of property T groups with these very different sorts of sequences?
So for property T groups, all sequences give expanders, and so in this way they're similar, but I think it'll be possible to construct. You know, if you just make the sequences grow in a very different way, and you can get things which are not coequivalent just by looking at the size, because obviously coequivalence would imply some relative bounds on the size of the equation. So you can probably do something which is a bit kind of cheating in that way.
Any more questions? Okay, let's thank Anna again for a lovely talk.